Hello and welcome back to biology. In this case, we're going to be taking a look at pulse and pressure. We've been learning a little bit about physiology, now taking a look at a little bit about the physiology of the heart. What is blood pressure? How is that controlled? And then also pulse. What is that? How does that work to keep you healthy? So let's take a look. First, blood pressure. When we're talking about blood pressure, what we're describing is the pressure of the blood on the arteries. Remember, the arteries are connected to the heart, and when the heart beats, when it's pumping blood out of the heart, there's a rush of blood that passes through those arteries. And we've already learned that they expand with each heartbeat, and certainly when the heart beats, there's more blood leaving the heart, so a higher pressure than if the heart is momentarily relaxed. And so there's really two different numbers that we keep track of when we talk about blood pressure. One of those is when the ventricles are contracting, the beat of the heart, and we call that systole. The next one is called diastole, and that is when the blood or when the heart is relaxed. And so you alternate between a high pressure, systole, and a low pressure, diastole, each time the heart contracts and relaxes. So that when we take a look at a picture like this, on this next page here we have the heart with the blood entering from the atria to the ventricles, so that right now the ventricles are relaxed. That would be a low pressure, and we call that diastole. When the ventricles contract, then the blood rushes out through the pulmonary arteries and also importantly through the aorta, and there's a rush of blood, so there's a higher pressure, and that would be systole. But then we lapse right back into the ventricles relaxing, so diastole again, it keeps alternating back and forth. These two numbers together, systole and diastole, are your blood pressure. And when we measure blood pressure, we put those two numbers over each other, systole over diastole. And so if you've had your blood pressure measured, you have numbers that are recorded for you, or if you're listening into a medical show, somebody's being wheeled into the ER, and they're calling out, oh my gosh, blood pressure is 140 over 80, and they're needing to rush around and get medication or do some treatment and everything. Well, what are those numbers, and what's a good blood pressure to have? In the case of blood pressure, good numbers, we're looking for numbers that are 120 over 80 or less. Obviously, too low is not good. 0 over 0 would be an indication that you are probably not alive. But 120 over 80 or less is a good target to have. To measure your blood pressure, they use a device called a sphygmomanometer. That's a fancy term. Meter means to measure. I honestly don't know what sphygmomana means, but in the end it measures your blood pressure, and here's how. The way it works is that you are hooked up to this pressure cuff. The pressure cuff is right directly over your brachial artery, and they fill the cuff with air. So it's going to squeeze that arm and also squeeze that brachial artery shut. They're also listening for that by using a stethoscope, so they can hear that there's no more blood flow going through this area. And it's at that point that they start to release that pressure. That's the part of the whole process. And what they're listening for first is the first time that they can hear blood. That's the maximum pressure that's needed to push the blood through the arteries. That's the top number, systole. And then they're listening for when that blood continuously rushes through the veins, the artery, and that's what diastole is. So two numbers, again, a high number over a low number when the heart beats and when the heart relaxes. 120 over 80 is a good target. Anything higher than that is an indication of high blood pressure. There's another term for high blood pressure, and that is hypertension. So if you know of someone who has hypertension or is taking medication for hypertension, that means that they have high blood pressure. There are some potential problems with high blood pressure. Chronic high blood pressure increases your risk for heart attack. It can also increase your risk for kidney failure. Your kidneys are there to filter your blood, but if they're constantly, especially that renal artery, under a lot of high pressure, you can damage the kidneys and cause them to not work. That's a very dangerous, life-threatening situation. Blurred vision. your shape of your eyes makes a big difference for your ability to see well. And with high blood pressure, it does change the shape of the eyes, causing your vision to blur. And you're also at risk for stroke, for bursting a blood vessel in particular in your brain. Those are all effects of high blood pressure. In addition to looking at blood pressure, though, today we're interested in looking at pulse. And the pulse is the beat of your heart. How many times does it beat within a given minute? And to measure your pulse, we're going to use one of two possible arteries. The one by the base of your jaw there in that diagram, of course, that would be your carotid artery. Or you can measure it on the thumb side of your wrist. That would be your radial artery. And I want you to honestly go ahead and do that right now. I know it sounds weird to be doing this when you're listening in on a presentation, but you're going to need to be able to do this as part of the lab that we're doing with the Pulse Lab. And the way that this is going to work is I want you to find your pulse, use your carotid artery or your radial artery wherever you feel it. For the carotid artery, find the base of the jaw and kind of work your way down about a ½ inch or so. And if you're really having trouble finding it, well, then do some jumping jacks and then sit back down here for a second. You'll feel that pulse. And what I want you to do is I want you to measure this over the course of 15 seconds. And so I'm going to give you a little bit of a countdown and say, ready, begin. That'll begin the time when you should start counting. And then 15 seconds later, I'm going to ask that you stop. So just like we're going to do in the lab, find your carotid artery or your radial artery. If you need to pause for a second, please do. Otherwise, we will begin in 3, 2, 1, begin. And that is the end, 15 seconds, so stop counting. That number that you have is not your pulse, that's the number of beats that you have for 15 seconds. Remember, your pulse is the number of beats per minute. And so if you're thinking this through, of course what you would do is you would multiply whatever number you have by 4 to get to your beats per minute. The average resting pulse for the average adult is somewhere around 70 beats per minute. So over the course of 15 seconds, we're looking at about 15 to 16 beats, 14 to 15 beats. The number for you could be slightly higher, could be slightly lower. It really shouldn't be too high. If you're calculating that you were at a rest beating more like 100, 120 beats per minute, something's not right. You may want to go back and double check this. In addition, if your number was less than 50, especially less than 40, then you're probably not measuring your pulse correctly. Try this again. It's important to practice this for the pulse lab that we do later on. When you're measuring your pulse, you're measuring the rush of blood through the artery. Again, you can measure your pulse, I guess, your heartbeat, just by putting your hand on top of your heart. But the pulse is technically what you're measuring through that artery. And again, each time the heart beats, a rush of blood goes through that artery, causing it to expand, so it kind of simulates that heartbeat. In order to know when to beat the heart, there's a process that's involved, and we kind of want you to be familiar with this process. The first thing to know about controlling the heartbeat is that there's a series of nerves on top of the heart called the SA, or sinoatrial node. The SA node is located on the right atrium. So here it is in this picture, same thing in this picture, on top of the right atrium. And these nerves receive a signal from a certain part of the brain called the medulla. The medulla is at the base of the brain, and through a series of nerves, there's a connection from the medulla in the brain to this SA node in the heart. And it tells or receives the signal to go ahead and contract. This signal is then passed on to what's called the AV node. The AV is atrial ventricular, and it's located between, as the name would suggest, between the atrium and the ventricle and on the right hand side of the body. This signal that's received by that particular set of nerves, the AV node, then causes the ventricles to contract. And so it's this loop between the medulla in the brain and the SA node and then the AV node, causing the ventricles to contract. Now this medulla part of the brain is a part of the brain that you really can't control. The medulla part of the brain is an unconscious sort of process, which is a good thing. I mean, you can control certain things like breathing and other things with your brain, and other times, like with breathing, you don't have to think about it. But your heart rate, you don't want to have to think about it at all. And certainly, if you were to pass out, you want your heart rate to continue. Excuse me. And so, how does the medulla know when to speed up your heart rate and when to slow it down? How does the medulla work? Here's a picture again. SA node on the top of the right atrium, AV node that then receives the signal from the SA node, causing the ventricles to contract. So how does the medulla know how to control the heart rate? First, inside your arteries are a set of receptors that are called baroreceptors. The prefix baro means pressure, like a barometer is a tool used in weather to measure the pressure in the air. Baroreceptors are little pressure sensors on the inside of your arteries, and they're connected back to the medulla. And so the medulla is constantly getting information about how much pressure there is inside your blood vessels. Kind of weird that we have to use a sphygmomanometer to measure your blood pressure, and yet your medulla knows how to do this all the time. When it measures the pressure, then what it's going to do is adjust your heart rate based on that pressure, but in what we call a negative feedback sort of process. In other words, if your blood pressure is high, it's going to slow your heart rate down, and if your blood pressure is low, if it decreases, then your heart rate will increase. In other words, opposite. When your pressure is high, your heart rate decreases, and vice versa. So negative feedback is the idea. Pressure in the arteries sent back to the brain as a signal. Your medulla then tells your SA node and then AV node ultimately to contract, to speed up, or to slow down. To kind of diagram this and give you an idea of what this looks like, what I've done here is I've taken some data on myself, and you're welcome to try this out in school if you want. I can give you the tools. Really simple device and works really well. And so this device that I'm using is being able to measure my heart rate, and that's shown here on the y-axis, ranging from as low as somewhere in the 50s to as much as 100 beats per minute or more. But I wasn't really doing anything active during this time. From this point here where I started collecting data to about the 100-second mark, I was simply standing. And my heart rate is fluctuating a little bit here, partly because I was trying to explain this to a class too at the same time. But so there I am standing, and my heart rate is up a little bit. And then at this spot here, all I did was sit down. Now when you sit down, you're taking all those blood vessels that were stretched out and you're compressing them. It'd be like taking a long garden hose and wrapping that up real tight real quick. You're going to increase the pressure inside that hose, and for me, sitting down, I increase the pressure inside my blood vessels. And remember, negative feedback. So as my blood pressure went up, my heart rate went down. The idea is that I don't have to push the blood around that hard. I've already got a lot of pressure. I've already got a lot of force going on. I don't need to give the blood a heck of a lot more of a push. All the cells are getting oxygen just fine, thank you, and so my heart rate can slow down. At the 200-second mark, all I did was go from a sitting position to a standing position. Oops, went to a standing position. There it is. And when I stand, I'm taking all those arteries and veins and I'm stretching them back out again, which is going to cause your blood pressure to decrease. When my blood pressure decreases, again, negative feedback, I'm going to increase my heart rate. So here I am sitting, and then I stood up, my blood pressure goes down, and my heart rate shoots up real fast, and then starts to level off. The reason why you would want your heart rate to increase in this case is that if you have a low blood pressure situation, then the heart or the blood's not getting to areas of the body that are going to need oxygen, in particular the brain. And so if your blood pressure drops suddenly, you'd want to increase the rate to kind of get that blood pressure back up again. And so again, baroreceptors, one way that the body has of knowing how much pressure there is, and better yet, another way of knowing how quickly to start to beat the heart, to speed it up or slow it down. There's baroreceptors and there's also chemoreceptors. Chemoreceptors measure chemicals. In this case, in the blood, there are nerves connected to the medulla that separately from pressure that measure carbon dioxide and oxygen levels. And by measuring how much carbon dioxide and oxygen is in the blood, the medulla then is able to make an adjustment and figure out how quickly to beat the heart. And so if your body has lots of carbon dioxide, for example, and that's something that we would need to get rid of, then your heart rate's going to increase. So measuring the chemicals in the blood, measuring the pressure of the blood, back to the medulla, back to the heart, to speed and slow the rate of the heartbeat. You're going to be adjusting the heart rate in the class as well. As part of this lab that I keep referring to, the Pulse Lab, you're going to be using exercise to measure heart rate. And certainly as you exercise, you're going to be changing the amount of chemicals within the blood, the carbon dioxide and oxygen levels, and so you're going to cause the heart rate to change. And certainly we would estimate that if you are exercising, your heart rate should increase. But we're going to take a look at how quickly it increases and also how quickly it gets back to a resting heart rate. And we're going to start to make some predictions about which individuals, or at least which groups of individuals, are going to be better suited to get to a resting heart rate faster than others. And so we're going to do a little bit of an experiment with this too. If you have questions at all, please don't hesitate to let me know. Otherwise, see you in class.